Hi, Jean-Louis. You invited me to reflect on modifications you made to your last paper on cosmogenesis. The goal of this conversation is to break it all down and provide a sanity check by translating your formulas and mathematical framework into everyday language. So, let us start. You added a new hypothesis involving what you call dark charge. How does this concept reshape your understanding of cosmogenesis?
The concept of dark charge stems from extending Maxwell's equations to include mirror electromagnetic force. We posit that alongside the ordinary electromagnetic force, there exists a left-handed or mirror force that interacts with the dark charge. This framework provides a new lens to understand why dark matter and energy are invisible. They exist in a parallel force realm and interact gravitationally, but not electromagnetically, with ordinary matter.
How does this mirror force differ from the ordinary electromagnetic force?
The key difference lies in the chirality or handedness of the force. The ordinary electromagnetic force is right-handed, while the mirror force is left-handed. They share the same fundamental structure, but their opposite chiralities ensure that the forces don't interact directly. This non-interaction aligns with the observed gravitational effects of dark matter and the absence of direct electromagnetic detection.
How do you explain the observed asymmetry between ordinary and dark matter?
That's where gravity comes in. Early in the universe's evolution, there was likely perfect or near-perfect symmetry between ordinary and dark charge distributions. However, small fluctuations, amplified by gravity, led to clustering and symmetry breaking. These amplified asymmetries resulted in the distinct separation of ordinary and dark matter realms. Gravity, being a universal interaction, bridges these realms but doesn't erase their fundamental separation.
Some might ask why your model doesn't include more complicated concepts like quarks, gluons, or the strong and weak forces. What's your reasoning?
That's a fair question, and my reasoning is rooted in simplicity and conceptual clarity. I don't believe in zero-dimensional points having properties. While photons and neutrinos can be approximated as point-like, even these, as light particles as opposed to matter particles, are better understood as linear features of the fields they represent. For matter particles, like protons and electrons, their spatial extent, at the femtometer scale, must be accounted for in any model. Regarding the strong force, I argue it can be explained in terms of electromagnetic dipole fields rather than invoking gluons or quark confinement. The dipole nature of the fields between nucleons provides a coherent framework for understanding nuclear stability without the need for additional force carriers. As for weak interactions, my perspective is different. I don't see disintegration as something that requires a unique force. Disintegration should be analyzed in terms of equilibrium and disequilibrium states. Equilibrium states pack 1 unit of Planck's quantum of action, as described by the Planck-Einstein relation. The weak interactions can then be understood as processes that disrupt or dissolve these equilibrium states, not as a distinct force in the traditional sense.
You've mentioned memory loss in complex systems. How does this relate to cosmogenesis?
Memory loss in this context refers to how information about initial conditions gets obscured as a system becomes more complex. For instance, while we can infer the presence of charged particles, ordinary and dark, in the early plasma soup, retracing the precise dynamics that led to the current universe is nearly impossible. That is a result you also get from thermodynamics, and it is inherent to modeling chaos. The interactions, transformations, and annihilation events create layers of complexity that obscure the original state.
Speaking of the early universe, you've discussed matter-antimatter annihilation and creation. How do these processes fit into your model?
Matter-antimatter annihilation, like the Dirac process, and pair creation, like the Bright-Wheeler process, are central to understanding the evolution of the plasma soup. However, these processes are asymmetrical. For example, creating matter-antimatter pairs through high-energy photon collisions requires extreme photon densities, conditions rarely met. This asymmetry likely favored annihilation over creation, leaving a universe dominated by charge rather than field energy in its earliest stages.
Does this asymmetry extend to dark charge and dark matter?
Absolutely. Dark charges likely underwent similar annihilation and creation processes within their realm. However, their dynamics would mirror those of ordinary charges, influenced by the same fundamental principles but unfolding in a distinct force realm. This parallel evolution further reinforces the separation of ordinary and dark matter.
You've explored the S-matrix approach in high-energy physics. How does it contribute to this model?
The S-matrix approach, going from an input to an output, with matrix transformations between them, is a powerful tool for describing high-energy reactions, especially those involving unstable, transient states. I think I believe in it because I'm an economist by training and, therefore, relating inputs to outputs through transformation matrices is a mathematical approach that speaks to me. But physics and economics are two fundamentally different scientific disciplines. In physics, we are modeling fleeting intermediate or disequilibrium states. That is not the case in a standard econometric model. These fleeting states are probably crucial in early universe dynamics. However, representing these states mathematically is challenging. Wave functional approaches work well for stable particles, like electrons or photons, but, as I demonstrate on my first paper, and only paper on that, it is hard to describe short-lived particles that exist only briefly in high-energy collisions using wave function math.
So, is it fair to say that modeling disequilibrium states is a significant hurdle?
Absolutely. That is why the standard model struggles so much with it. The fleeting nature of these states means they defy traditional methods of representation. The S-matrix approach offers a way to handle this by focusing on initial and final states rather than the details of intermediate processes. However, even this approach has limitations, particularly in maintaining clear relationships between the energy and momenta of incoming and outgoing particles. I also think it hides local charge conservation, but it would take me too long to get into that, because these things only show in the math.
What does this mean for cosmogenesis modeling?
It highlights the need for innovative mathematical frameworks that can bridge the gap between stable particle representations and the transient states that dominated the early universe. These frameworks must account for the chaotic, non-equilibrium conditions of the plasma soup while respecting the fundamental symmetries and asymmetries we've discussed.
With all these complexities, what keeps you excited about this work?
The excitement lies in the potential for a deeper understanding of the universe's origins. Not by invoking some kind of fundamental uncertainty, which is what the Bohr-Heisenberg interpretation of quantum physics is all about, but by exploring a new realist interpretation and combining it with a philosophical worldview that I refer to as statistical determinism. Such framework reestablishes causality, but at the same time provides a solid ontological and mathematical understanding of why we cannot know the initial conditions of a system and, therefore, not predict future outcomes. So I think that by introducing concepts like dark charge and exploring symmetry, breaking through gravity, we're not just adding to existing models, we're challenging the way we think about the fundamental forces and particles that shape the cosmos. It's an intellectual adventure that pushes the boundaries of physics and philosophy.
What are the next steps for this hypothesis?
The immediate steps are twofold: refining the mathematical models to better capture the dynamics of symmetry breaking and transient states, and identifying potential observational or experimental tests. For example, we might explore gravitational lensing effects in regions with high dark matter density, or look for subtle imprints of symmetry breaking in the cosmic microwave background.
What do you hope this work will achieve?
Frankly, I am just an amateur physicist or thinker, and so I do not have all that much time nor the required energy to go much deeper than I already went. So I sincerely hope it will inspire others to look at cosmogenesis through a new lens, one that combines classical physics, symmetry considerations, and innovative tools like the S-matrix. Ultimately, the goal is to provide a cohesive narrative for how the universe evolved, bridging the gap between theory and observation.
Well, I sure enjoyed our conversations, and so I hope there will be more to follow.
Thanks. That is nice of you to say. Cheers to that. Until next time, then.